Welcome, ladies and gentlemen. I'm Dr. Dilda Chowdhury, Director of Strategic Marketing, Power GaN in Nexperia. Our topics today is Power GaN technology for mainstream power conversion applications. So in the brief, the power technology for the mainstream power conversion applications, whether it's a small or big, power GaN devices coming with a very disruptive high performance in mind is giving the opportunity to take the technology into the power conversion applications. And along with the very fast semiconductor device, it comes with the complementing copper clipped technology where we have got a huge experience of over 20 years of experience in Xperia, and then it's showing the best performance, whether the application is in server computing, industrial automation, telecom infrastructure, or automotive. At the same time, from the volume, cost, performance spectrum, Power GaN FETs are right at the top with a silicon-based manufacturing infrastructure, and larger diameter wafers like 80-inch wafers is just down the line as possible to support the demand. Power GaN products and manufacturing aggressively addressing the volume and the cost to support the strong mainstream demand. Just to having a quick update from the market development, we know that there is a strong adoption of the battery electric vehicle, accelerating the adoption of the wide bandgap devices. Mild hybrid electric vehicles are growing until 25, but after that, there will be a time of stagnation where the higher voltage platforms will be developing much faster. The US regulation updates coming much earlier than anticipated, and forecast indicates that 26 to 30%, the 20 to 30% will be the electric vehicle versus 42% as originally anticipated. There is an increasing trend of moving the 800-volt systems for the luxury electric vehicles, while the low-cost electric vehicles will remain in the 400-volt platform. And because the 800-volt offers lots of benefits that we'll be discussing. Nexperia have been working with the Power GaN technology for a while now, including our research to bring the product in the commercial entity. Our ambition is to grow to be the market leader. We already embarked on the third generation of 650-volt Power GaN platform and offering a benchmark performance at a better cost. Our controlled production flow and aggressive cost down roadmap and dual sourcing strategy would be helping for our customers to have a smooth transition to Power GaN technology. The path to growth for Power GaN technology is early sales coming from the industrial, higher than 1 kilowatt power supply, titanium grade, UPS, battery storage, PV inverter, high-end D-class audio amplifiers. While we are supporting the industrial applications, including servers, the automotive applications like onboard charger, DC to DC converter, auxiliary power, and traction inverter will take the advantage of this Power GaN technology. Starting our first generation released in 2019, we are working on now on the generation 3 to be released in 2023, taking the RDS(on) of the products down to 5 million within the copper clip power technology. Why the Power GaN devices is most suitable for the mainstream applications? Because the whole infrastructure for the GaN is on GaN on silicon, which help using the existing silicon-based fabs, simpler processes, easier production, easy to scaling up. The number of wafer output or the scaling up on the wafer size is much more easy on the silicon-based infrastructure. And we have got many wafer fabs where we can easily transfer the process, while we are currently considering dual sourcing wafer fab. The volume supply, established supply chain would help supporting the mainstream high demand. We go for the cascade structure for our device because it helps getting the highest electron mobility and the best figure of merit. More efficient, it is simple to drive, easy dead time control, and robust gate drive. Robustness and reliability is another aspect going in bringing the power GaN technology. The devices has got the higher transient overvoltage capability, plus minus 20 volt gate rating, 4 volt threshold, robust structure, robust gate, and ACQ 101 qualified along with some power GaN specific reliability, and complemented by the copper clip CC pack technology, where we are only using copper clips. There is no wire bonding. So that helps the robustness of the package for the packaging point of view, and also the board level reliability. Top and bottom side cooling options, low package inductance, reliability over the wire bonded packages, and lower package resistance and inductances. How the GaN contribute to the challenge? So we need to think beyond performance. Obviously, GaN offers the best performance without any doubt. Industry's experts are aligned on that one. They're in agreement. But at the same time, the reliability, the availability, and the cost, these are some of the key parameters that we need to think about taking it forward, along with the supply resilience, where you'll have to have the platform that can support the rapid demand. The Cascode GaN enabler offers four major benefits. One is the system cost down, easy to drive, and lower losses, and gives the best efficiency. So it brings all the high performance enabler along with the robustness in the supply chain resilience. Technology options. While we are bringing the power GaN technology, we know that there are other technologies, incumbent and the contemporary technologies around available, like silicon superjunction, IGBT, silicon carbide. And as you can see, all of them has got certain sweet spot, and depending on the customer requirement. As the frequency and the power goes up, and the power GaN devices are quite nicely positioned and continuously pushing the boundary. While we see there are lots of applications and the products available for the low power GaN, we can see that the high power GaN, the GaN is penetrating slowly. Within the voltage spectrum, power GaN devices are very well positioned for the 650 volt, for the 400, 500 volt platforms, for a wide range of applications, which I'll be covering in my latest slide. While the silicon carbide and the IGBT is currently still supporting the higher voltage grade, while power GaN is continuously pushing its boundary to increase the voltage, increase the power, while giving the best compromise of the performance, cost, and availability. Just to refresh what the GaN positions, if we look at the GaN has the, compared to silicon and silicon carbide, GaN has the highest band gap, higher critical electric field, higher electron mobility, and a good thermal conductivity, and a very high saturation velocity. As a result of this one, GaN has the potential to offer the lowest possible RDS on in best possible switching performance. So in summary, GaN can offer the highest speed, lowest the carriers within the device need to travel the lowest distance because of the highest critical electric field and band gap, and the fastest turn on and off performance. And these are the three key performance indicator within the GaN that makes it unique in the disruptive wide band gap technology realm, where the application can get the biggest benefit. For the higher power, our GaN Cascode is in a best suitable platform, and because it also gives a very good high temperature performance, lowest turn-off losses, about 3 times lower reverse conduction if you compare against E-mode or silicon carbide. And Cascode has the 2 times the pulse current capability. The most interestingly, the Cascode offers the first and third quadrant and also the pulse current capability as good as the forward and the reverse conduction. The Cascode has the high threshold voltage, which gives is the design margin not to compromise for the gate bounce or the shoot through concerns. Cascode has a larger VGS limit, and it's got a very low leakage current. The Nexperia GaN Cascode brings lots of benefits. As you can see, it has got a 650 volt HEMT device along with a driver, a low voltage silicon device. And the advantage of this combination within the CC pack, we cascaded that one and putting the silicon devices on top of the HEMT device so that it's almost like an integrated device. And it gives the plus minus 20 volt gate rating, high threshold voltage 4 volt, and easy to drive 0 to 8, 10, or 12, very forgiving. Low thermal resistance and ultra low package inductance, TJ max of 175, qualified to JEDEC and ACQ 101, and very low third quadrant loss. That's why the first and third quadrant current carrying capability is not compromised. It has the same current carrying capability. Extremely low switching losses with excellent dynamic performance. And we have got a top and bottom side cools, multiple packages available. The driving the Nexperia Cascode is very easy, and it doesn't need any negative voltage to drive it. And soft driving is good enough, and we don't need a very high current drive. An easy, flexible drive like some of the simple Silicon Lab driver is good. And one of the big advantage, we don't need a regulated driver voltage. So if the drive voltage is variable and it's still okay, easy bootstrap unregulated driver is still okay for the driving. So that makes the design very simple. GaN has got, as I mentioned, the high threshold helps avoiding any parasitic turn on. Low gate charge, so low drive power is required. High VGS margin, full conduction, already possible at 8 volt. Don't need to drive it too hard. Enables use of standard silicon FET drivers. No tight voltage regulation required. So it enables bootstraps simple supply for and reduced bill of material. So there are certain key advantages from the technological point of view. One is the lowest hard switching losses. It doesn't have any QRR, so it can switch really fast. Lowest soft switching losses compared to the silicon carbide and other GaN platforms. And the lowest third quadrant losses, you can see, and 1.3 volt compared to 5 and 4.6 volt with competitors GaN and competitors silicon carbide. So it helps very forgiving dead time control, lowest reverse recovery losses as well. So as a consequence, we can get the highest efficiency, higher power densities, and lowest power losses. So it gives the excellent hard switching performance. Some of the switching waveforms taken in our lab, and it shows on the right-hand side the turn-off losses. Our GaN offers the lowest, the green line showing the lowest switching losses on the hard switched configuration. So, and then here is another one just showing that the Nexperia again has got the highest DIDT and DVDT and offers the lowest switching losses in the hard switch performance. Similarly, on the soft switch performance, Nexperia again shows the lowest switching losses. So these are the as a consequence, can get the highest efficiency. It offers the lowest reverse recovery losses, as highlighted. But one of the things that sometimes the silicon carbide world says that silicon carbide has got a very high thermal conductivity. But unfortunately, as the temperature goes up, silicon carbide has got a much lower thermal conductivity. Thermal conductivity goes down as the in the black line shows that as the doping of the silicon carbide device increases, the thermal conductivity goes down even further. At a high temperature like 150 or 175 degree, the thermal conductivity between GaN or silicon and the silicon carbide is not significantly different. One of the apparently disadvantage of the silicon GaN devices is that the temperature dependent RDS(on) goes up much faster than the silicon carbide, but it has got an advantage. Even though you can design for the highest temperature, but at all the normal operating lower temperature, the GaN-based system offers the lowest losses on the conduction losses as well as the switching losses that gives the best possible overall system performance. Sometimes there is a discussion about because it has got a low voltage silicon whether GaN suffers at high temperature, but it isn't because the low voltage silicon has got a very low drift region. So at you can see that on the 2300 degree and 150 degree reverse recovery and the switching waveform doesn't compromise at the whole temperature range with no snappy or sluggish behavior. So as a consequence, you can see that when you compare around competitor silicon carbide devices with our GaN devices, our GaN device right up to 12 kilowatt shows significantly higher efficiency in a configuration with the half bridge, which is the integral building block of many of the power conversion. And this one is done only at 70 kilohertz for 240 to 400 volt conversion, and with almost 46% lower on driver losses and about at 11 kilowatt 25% lower losses overall, even though at 175 RDS(ons) are the same for both devices. In summary, higher power switching applications can benefit from power GaN technology because of the high current carrying capability, low RDS(on), lowest hard and soft switching, high DVDT, DIDT, lowest QRR losses, high temperature switching tails, low driver losses, lowest dead time losses, and lower thermal resistance, optimum performance, and higher power density. And there are many other white paper, application notes, and others available in the nexperia.com. GaN is suitable for 650 volt, as you have mentioned, a wide range of applications like custody, power supply, DC-DC, and OBC, and the CC pack is rightly well positioned within that spectrum. And you can see that from 50 million right down to 5 million devices and the bare die are currently within our portfolio to take it forward. There are a few applications, bidirectional PFC application where GaN can give the biggest advantage for the 400 volt system for sure, and for 800 volt system. Obviously, there is a silicon carbide competitor along with the multi-level GaN devices can also support within that spectrum. The moving into the soft switching applications for the 400 volt, the power GaN devices are well positioned. For 800 volt device, there is a multi-level conversion that we are currently working on. So the copper clip technology brings all the benefits that I have already highlighted. The copper clip, the thermal performance, the top and bottom side cooling option, and manufacturing robustness brings the copper clip CC pack and very well positioned along with the power GaN device. And the copper clip technology offers like 2.37 nanohenry inductance compared to almost 13 nanohenry in the leaded packages. So it gives a significant advantage. And we are also joint collaboration work with Nexperia, with the Kyocera AVX to bring the module work and in a half bridge form for the higher power applications like traction inverter. And some of the demonstrator using our CC pack shows that 35 kilowatt GaN based inverter gives significantly higher efficiency. Also working with the Ricardo for the higher power traction inverter and some of the results will be available in the Q1 in 2023. Higher voltage applications we suggest for the multi-level inverter on the efficiency, cost, power density, power quality, and reliability, fault tolerance, and design margin and cooling options. The multi-level can bring significant benefit. And there are certain multi-level converter applications where the 650-volt GaN devices can be used. And obviously, multi-level inverter helps getting the higher blocking voltage, and also at the same time better power, and switching waveforms gives much lower EMC and EMI. So for more information, you'll be able to get it from the nexperia.com and GaN FETs. And with that, thank you for patient hearing. And if you've got any question, thank you.